talking about this thing, synthesis for design. So remember that we took this example of metal casting, and what happened is that we discussed more about the heat transfer aspects. Okay, so there is an insulation, there is a mold, and then you pour the molten metal, and the molten metal will solidify. Uh, so molten metal will solidify, and we discussed about a little bit about heat transfer and also the properties like thermal conductivity, specific heat, and all that, how these things are important. Now, when we are talking about design of that particular system, it's not enough to just talk about heat transfer. So you will have to also talk about, since it's a casting that is coming out, you'll also have to talk about the strength of materials and manufacturing aspects, various manufacturing aspects, metallurgy, things like that. So this we discussed yesterday. So what we need to do is do synthesis. So for example, if you have a heat exchanger, as I mentioned yesterday, there is a thermal design of heat exchanger, but there is also a mechanical design. Mechanical design takes care of strength of materials. It also can be, it also can also include some vibrational aspects and things like that. And then you have to also think about other aspects like manufacturing and the ability to clean the tubes. Let's say it's a shell and tube heat exchanger, stuff like that. So what I'm saying is that various aspects have to come together and they have to be synthesized. And when it comes to synthesis, this is the definition I told you that I picked up from Cambridge Dictionary. So it's like the act of combining different ideas or things to make a whole. Okay, so make a complete thing with the help of ideas from different things. So thermal design, strength of materials, manufacturing aspects, stuff like that. So this is an example. I said that let's talk about a musician who's making an album. So there is a synthesis of African and Latin rhythms that he's making to come up with new scores. Okay. Now, so information from different types of models come in, and they will use maybe experimental results and also numerical results, and these existing systems are incorporated into the design process. So in the process of doing all this design, there will be some experimental results, some numerical results, everything have to be put together to come up with the whole design. And as I said, cost of materials, properties of materials, characteristics of materials, these things are also important. Now everything together will give you the design. So material selection is also a very important factor. You know, which material you choose. For example, which material you choose for the heat exchanger tubes, which material you choose for the shell of the shell and tube heat exchanger. And there are other aspects also part of design. It's not just like you as engineers, you come up with a design and that's it. It cannot be that. So there are other aspects. For example, there are safety aspects, there are legal aspects, regulatory aspects, environmental considerations. Those are also important. Now, to illustrate this, just to take a look at this one. Okay, so this is a seat belt, right? So if you are making a car, that's a safety aspect. And is it a legal requirement? It's actually a legal requirement. You know, so when somebody is driving, the driver and the passenger, they have to use a seat belt, and in many countries, even the rear seat occupants, they also have to use seat belt. Okay. What about this one? If you look at this, do you understand what this is? Let's say I don't tell you anything. You just look at that photo. Tell me what this is. Brake light is actually written, but why is this highlighted?
Safety aspects.
Safety aspect, correct?
Red light, we can see clearly the red
Yeah. So there are lights here also as you brake, isn't it? They also glow. But what is the importance of this one?
Sir, when you actually brake, the third light glows. The other lights also glow as well when you turn on the lights in the night while driving. So that is to, matlab ki, that is to warn the passengers in the rear that I am actually braking and not this is for the matlab ki, illuminating
Not for
the
turning,
surroundings.
not for turning or anything.
Yes.
Not perfect. Yeah. So if you are the driver of a car which is just behind this, then it's much more likely that you will see this light because it's right in the middle of your field of view. Okay, suppose you are like in the same lane, driving just behind this, you will be able to see this. You're much more likely that you will be able to see this. Okay, your eyes will not probably go this way. You might see this also, but more likely you will see this. So this is a safety aspect which didn't used to be a feature in automobiles for a long time. So there are people, there are safety experts who thought about this, who campaigned for this, and then it has become a regular feature. Okay, I'm not very sure whether it's a legal requirement. Probably not in India. Okay, so you can still make cars like cheap cars which do not have this one, I think, but I have to, the legal aspect I'm not very sure. But that's not the point of this course. So I mean, if you have interest, you can check this out. But better cars, more higher end cars will definitely have this one. This is like this show the Hyundai Elantra. Okay, so this is kind of like more expensive car and it has this particular feature. So when this glows, this is a safety feature. Now, so these are aspects which have to be built as part of the design. Now, what's this? So this is obvious, right? So there used to be a BS4 and then BS6 came into operation from 2020. Okay, so last 5 years or so it's been around. So here you can see, for example, BS4 didn't have anything on the particulate matter thing. Okay, whereas BS6 specifies that you can do only this much of particulate emission. So this is for petrol vehicle, this is for diesel passenger vehicle, and this I'm showing you just to let you know that again, just making a design, just making a car is not enough. Okay, there has to be, as I said, safety aspect, previous slide, and there is also legal requirement, and there are environmental regulations which you have to be able to follow. Right. So we will actually not be doing many of these things in this course. If we try to do everything, design has many aspects. If we try to do everything, then we will not succeed. Okay, so just become too difficult for us. Will not be able to cover. But this is just to give you this exposure that these things are important. So I said safety, legal, regulatory, and environmental considerations. Then let's also think about typical design procedure. Okay. This I think you can understand based on our previous lectures, previous discussion. Okay, so you have to have an initial design. There are some inputs like, for example, the inputs in that first example in the course that was like, okay, this much amount of flue gases are coming out from the DG set, and then the flue gases are at this temperature, this much is the flow rate, and you want to utilize it to produce steam. Water is available at 10 degrees Celsius, and steam you wanted at 2 bar and saturated vapor, that sort of steam. So whatever it is, based on that we chose an initial design which was a finned tube heat exchanger, right? And you come up with some design of that one. Okay, you have some requirements, okay, that you cannot allow this much, more than this much amount of pressure drop, and you have to get this steam and all that. So you get an initial design. So once you have that initial design, you analyze and see whether that initial design meets your requirements. Like, does it actually give that steam? Does it meet the pressure drop requirement and things like that? So that part is the analysis. If you remember our last class yesterday, the point that I made is that there is a difference between an analysis problem and there is and a design problem, right? Analysis problem is typically what you do in other courses, like maybe if you do a heat transfer course, you just do calculations for a problem which is defined in a given problem. Okay. Now you analyze this and you evaluate the design, and let's say pressure drop is a criterion. You have to keep pressure drop below a certain value, because as I discussed yesterday, more pressure drop means more pumping power, which requires more expenditure. So you see whether it's acceptable. Is the pressure drop okay? If it is not acceptable, then you go and redesign. That means you change something. Maybe you change the dimensions. Maybe you change the material. Okay. And if it is acceptable, then you come here. Now there's one more thing, that when you do this analysis and evaluation, there is also some inputs apart from the initial inputs of, you know, the steam flow, steam temperature, water requirement and all that. You also have some more inputs which go into this process, which are about the components, material properties and experimental data. Okay. Whatever experimental data in this context can mean the flue gas temperature, flow rate, okay. Some information on properties like thermal conductivity, specific heat and all that. Okay, I think you can understand this. So this shows that design is not a unidirectional process. You might have to go back and do this again. So iterative process and improve the design, and finally you have an acceptable design obtained. Okay, now there is another important thing. We will also talk about selection and design. Now this is what? Thermal power plant. This is schematic. So if you look at this, this will be familiar to you. Maybe you don't know everything about this, but you kind of can interpret most of the things here, right? So for example, you have a condenser, you have cooling tower, you have boiler, okay, and of course you have turbine. So turbine can be also in different stages, you know, low pressure, intermediate pressure, high pressure turbines, but those things are not shown here. This gives some amount of details. So let's say you want to have a thermal power plant, right? So you have identified the land, you think you can get water there, thermal power plant requires water, right, because you need water here. So let's say there is a project which is there for which you have to design this thermal power plant. Now one thing that will strike you is that you will not be designing everything from first principles. You will not be designing everything from scratch. What do I mean by that? If you want to set up a thermal power plant, then you can't say that, okay, you will design boiler from the very basics. Okay, that this much amount of flow rate of steam is required. For that I will burn this much amount of coal, and for that this will be the tube material, tube design, everything, you know, everything you cannot do. Similarly for turbine, every single thing like turbine blades, how the turbine blades will be, what will be their geometry, what will be their material, you cannot do all calculations for turbines, right, when you are in charge of, let's say, designing a thermal power plant. So what will you do? You will buy some items, correct, and put these items together to give you a complete design. You understand what I'm saying? Right. So there are some items which are kind of, you will have vendors which will supply, who will supply those items. So for example, if you are able to say that, okay, this much steam will go to turbine and this will be the kind of temperature and pressure and all that, and this is the overall requirement of the plant, then you can prepare a data sheet which gives you the turbine specifications, and those based on those specifications you can float a tender, and then people can bid for a turbine, order, and then whoever gives you the best offer, you give that order on them to supply the turbine. Okay. So designing a thermal power plant doesn't mean you design everything from scratch. Similarly from boilers, similarly from even coal handling plant and ash handling plant and all that. Then what do you do if you buy everything? Actually, you don't buy everything, because you will still be doing designs for various things, like how much capacity the pump needs to have, what will be the flow rate of the pump and all that. So you do an overall design in which you fit various things. Okay, various things which are available. If something is not available, some component is not available, then maybe you have to design that also. But typically for this case, you do not do a component level design. You do a more of a system level design. Okay. Now with this in mind, with this picture in mind, let's look at this text, that this is a selection versus design issue that we are talking about. So selection means determining the specifications of the item from the requirements of the given task. So you prepare a data sheet which tells you, okay, this much flow rate, this much pressure, this much temperature, whatever. Now design, on the other hand, it starts with the basic concepts and modeling, evaluating different designs like that previous flow chart that we saw. That's a more typical design thing. Okay. Now to illustrate this a bit better, let me go to this one. This is a website of KSB Pumps. KSB Pumps, actually, no, not just pumps, I should say KSB. Okay, and it has various things, like you can see pumps, valves and all that. Okay, so you can, if you go to the website ksb.com, you can see a product catalog. You can see pump, you can see valves, you can see mechanical seal, valve actuator, valve automation and all that, various things. I have not explored everything here, but let's say you choose pumps, then you will see this one, this is submersible motor pump. This is a more usual kind of pump, and this is vertical single stage fully floodable submersible pump. So there are various varieties of pumps. So these are people who have worked on pumps. They know the fluid mechanics of pumps. They have been working on this for a long time. They have their designs. They have chosen the materials. They made these products. These products are available. Okay. So your job, if you are making a plant, then you say that, okay, this much flow rate, you want this much of pressure rise, whatever will be your requirement, then choose a pump. This is my application. Maybe your pump handles corrosive liquid. Then you look for a pump which can handle corrosive liquid, right? So similarly for valves. So valves are, you saw valves in the previous schematic also of the thermal power plant. So valves are everywhere in these kinds of systems. So this is a gate valve, this is a check valve, and then this is a butterfly valve, like that. Okay, we don't have time to get into all this, but this is a globe valve, right? You must have seen a valve like this, correct? So all these. So you choose all these, and this is, I am showing you this just to tell you that when you are in industry, then this is a regular feature of your job. That okay, there is something, some requirement. You go and choose various things and see whether it will fit your overall picture, whether it will fit your requirement. So you can do these sort of things for other stuff also. You can this is just one example, but you can maybe look for heat exchangers. Maybe you can look for heat sinks. Maybe you can look for accumulators, absorption tower, lots of things. So I hope you understand what is the difference between selection and design. Now in India, I have to say that most of the time selection is more important because there are many things that we do not make very well in our country. Of course, you can understand, right? We are not leaders in products of any kind throughout the world. So, but we oftentimes we buy and put things together. So selection is quite often more important in the Indian context than design. Okay, so if you are designing an Apple phone, then you work on the basic design, right? Quite a bit. If you work on a very high-speed computer, then cooling requirement in that computer is also maybe you have to do some design from the basics because it dissipates a lot of heat for which there are no ready-made solutions. So maybe you have to invent a solution out there. So that is like more challenging thing where you're not buying things and putting together. So in design, okay, you have a basic concept. Then you make designs, evaluate designs, and ultimately you fabricate the particular design, the final design that you arrive at. But then you also have to carry out tests. I didn't talk about tests previously. So you carry out tests to make sure that that particular design actually works. There is no other difficulty associated with it. Then it can go to production. That's the whole process. So design is directed as creating a new process or system, whereas selection is just choosing the right item. So this is one example that I had shown you, and this is another example of some chemical plant. This I am showing you just to show that apart from thermal power plants, there may be other kinds of systems that you might have to work on. You can, when you look at this, one thing that strikes you that it has got lots of pumps. For example, this is a liquid absorption pump, the mud pump, the discharge pump, circulation pump, whatever, many pumps. It's got an absorption tower, which chemical engineers more frequently deal with, and there are various kinds of tanks. Okay, there's a lime slurry pump. So various things. Whatever we teach you in IIT, that's not going to be sufficient when you work. Okay, that's you have to know that. You have not seen anything like this previously, I suppose, isn't it? But when you, if you join this particular company, maybe on the first day you will see this. Okay, so what is your response? Your response should not be that, oh, I don't know anything, IIT didn't teach this, IIT is useless. Now that hopefully is not your response. So your response should be that, all right, let's see. Do I understand something about pumps? Do I understand something about tanks? Do I understand anything about absorption power? Maybe I don't know, but maybe I can read this up. Maybe I can speak to a chemical engineer. I can figure this out. After all, this will also have mass conservation, momentum conservation, energy conservation, and all that. So I can understand this. So you can also have you have to have that sort of an attitude to be able to fit in to an industrial perspective. Okay, so this talks a little bit more about the selection versus design. So there are heat exchangers of different kinds, and we might have to choose a particular heat exchanger for the application that we are interested in. All right, now we'll talk about optimization a little bit. We have already talked about optimization, but let me repeat some aspects of this. So we know that there is a design, and we know that there can be multiple designs for the same kind of purpose, right? For that heat exchanger which we are talking about, there can be multiple heat exchangers, multiple possibilities. And how do you choose this? As I told you, the choice has to depend on two things. One is that there may be some constraints, okay, that maybe you have a constraint of money, maybe you have a constraint of space, maybe you have a constraint of material that you can use. So subject to those constraints, you also have some objective function which you are trying to optimize. So you might like to maximize or minimize some objective function to be able to arrive at the optimized design. So the objective function can be, okay, you try to maximize profit, you try to minimize cost, you try to optimize product quality. Okay, so if you want to maximize profit at the expense of product quality, that will not work, hopefully, right? The consumer will say that, okay, your product quality is so bad, I'm not going to buy it. And there may be some output things that, for example, the temperature at which something comes out, that needs to be optimized, okay? Stuff like that. So these are some practical aspects of this. Nowadays, it's difficult to monopolize a market. So if you are making a phone, for example, if you are making a mobile phone, then of course it's like, it's impossible to imagine a situation that you have monopoly, right? Even if you're making something which is less popular, more industry relevant, let's say heat exchanger or pump, you will not be able to monopolize this. Your product will typically not be that superior to other products in the market, so that everybody buys just your products. That will not happen. So this is the product is going to survive. Basically, if you broadly see, the survival of a product is largely a function of the performance per unit cost. Like I'm going to pay some money, how good is the performance? So performance per unit cost is going to matter so much. So optimization of the manufacturing process is actually to get the best quality per unit cost. Right. So as I said, optimization based on objective functions. So the objective function can mean weight, size, efficiency, reliability, etc. Also, it can be profit, it can be cost, as I mentioned, but it can also be size. Okay, for some applications, for example, there's an aircraft engine. Can you make it very big? It will not work, right? It has to be within some space constraints. Efficiency also has to be maximized in some cases. Reliability, it should not fail easily. You make something which is very good, gives you very high efficiency, but after 6 months it fails, then it will not work. Refrigerator example, for example, refrigerator case. Refrigerator, various systems are available. I think you all know that there can be a vapor compression system. There is also a vapor absorption system. So if it is a vapor compression system, we have to think about components like compressor, condenser, evaporator, valve, and these can be designed or selected based on a wide range of specifications and characteristics. There has to be also, in a refrigerator, there has to be a control system also. control system to control the flow of the refrigerant and things like that. So the or the compressor performance, so these things you require all these things. So the control system and the operating conditions can also be varied, and the inside geometry in a refrigerator, inside geometry, dimensions, materials, these things are all important variables. So we discussed all this. There can be acceptable designs, workable designs, and out of those we get the optimum. But it might, for example, if you go to a shop to buy a refrigerator, you will see some energy rating of the refrigerator. So there's a Bureau of Energy Efficiency, BEE. So that gives you some kind of a rating. So there is 5-star rating, 4-star, etc., whatever. So those have to be. That's also part of a regulation that you have to have some kind of a rating of on the refrigerator. So you have to be able to optimize the design to get the best product quality per unit cost, as I mentioned, but also at the same time you have to meet this requirement of energy rating. Then this I briefly mentioned that there is after you fabricate there will be testing and production. Okay. Once you make something, let's say refrigerator or a heat exchanger, whatever, then you have to also test it to see whether it actually delivers what you designed it for. Now the overall fabrication and assembly of the system is under the control of the design group or a project manager who coordinates the design and engineering activities and may oversee the development of a prototype. Okay. And once the prototype is obtained, it's subjected to extensive testing, and we also sometimes test it for conditions which are much worse than expected in normal use. Okay. So those are performance tests. And with those performance tests in harsh conditions, we see whether the product will actually do well under conditions which are away from the normal conditions also. Some tests can also be like destructive sort of tests. For example, batteries. There is a lot of importance on batteries nowadays. So you know, for example, that buses nowadays in Delhi by 2030, so in about 4 years from now, all buses are going to be electric buses. Now you still have CNG buses, but those buses will be phased out. So when you have all electric buses, we'll have to be very sure that they work well. Okay? But you might have also heard about these buses catching fire. Have you? Okay, you might have seen that. Many cases have happened in Delhi also. Right? So batteries are like an evolving technology, and many batteries in these buses also, mostly they are imported. Okay? They are imported from China or maybe from other countries. So some tests are done on those batteries in India. After bringing those batteries, some tests are done also. So just to give you an example of the kind of tests that can happen, one can also puncture a battery and see what happens. Now normally puncturing will not take place in normal operations, but let's say there is some impact, something happens and the battery gets punctured, then what happens? Okay, so such tests are also done, and to see how safe these systems are. The other point which you can see is that there are sometimes accelerated tests. Now accelerated tests are, let's say you have some fluid which is being run in a closed loop in some heat transfer system. Now that if you run that and the fluid experiences high temperature, okay, so maybe let's say it can work well even at temperature of 200 degrees Celsius. I'm just throwing up some numbers. Okay. But if you use that same system, see that same fluid is like getting heated, cooled and all that. So it's 200 degrees Celsius, then it comes down to 25, again gets heated to 200. So there is a cycling process which takes place, right? Getting heated, getting cooled, again getting heated, getting again cooled. So this thing will, as you can imagine, result in some deterioration of the properties of the fluid. Right? The fluid might not work as well if you use it for maybe several years, or maybe 5 years, 10 years, I don't know, it depends on the particular system. So if you are making this fluid, so there are some fluids called heat transfer fluids which are used in these systems. So if you're making these fluids, then you have to kind of say something about how much will be the life of this fluid. So I'm making a plant, and in that plant I want to use your fluid for 10 years. If I want to buy that fluid from you, then you have to be able to give me some guarantee that it will last for 10 years. But how do I do that? See, if I'm the manufacturer, how do I say it will run for 10 years? I can, other kinds of products, let's say there is a pump that you make, okay, you run the pump, you fabricate the pump, make the pump, and it gives you the height of rise in height of the fluid that you wanted. So that you can test easily. But how do you test a fluid like this? So there are some accelerated tests which will tell you whether the fluid is going to last 10 years or not. So there are special test protocols which will tell you that okay, it will last 10 years, right? So these are various kinds of tests. Now you make a prototype, fabricate a prototype and do these tests, and after prototype development and testing, the system goes to production. Right. Production also, you have to make sure that you have chosen the right processes, and the production processes should not make the product too expensive. Let's say you made a very good design, but if the production process is not very good, the product becomes too expensive, or there is some problem in the product. So everything is integrated together. This is the entire picture. One more thing, since I am showing you a lot of text, I will repeat what I told you in the last class, that in class don't try to read the text that we have. Just wherever I take my cursor and whatever I am speaking out, just follow that. This PPT is for your consumption after the class. Right? Okay. Now we told you about design. We told you about synthesis and design. We told you about I told you about selection and versus design. Now, where does design fit in the entire engineering enterprise? So this I have taken from this book by Jaluria, which I mentioned, Yogesh Jaluria's book, and this is a flowchart. Okay, so I'll give you 1 or 2 minutes to have a look at this and see whether you understand this. This is kind of small, but are you being able to, from last row, being able to read this? Okay. So this is the design part, engineering design. if you make a design, you test it, and if it doesn't work, then you redesign, come back. Then if the design becomes acceptable, then you optimize it, and then after that you do fabrication and testing, and you do the production and sales also. Right? This is the entire picture. But before all these, you also have to see need for opportunity, right? Like, is there really a need for product? There are many such products like this in the market, and so that's a market analysis. Then as a feasibility study, if it is not feasible, then terminate the project. Don't proceed. If it is feasible, then so that's just a feasibility thing. Then you do some research and development, and that goes into your design also. Okay. And even when you optimize that stage also, there is some interaction between research and development and optimization. Okay. Now we do not have much time. We have maybe 7-8 minutes here. We'll just look at some examples. Example of thermal systems. We'll do this quickly because already we have seen some examples. Now this is a continuous casting process. So you have liquid metal which goes into this mold which is water cooled, and there will be solidification, right? Others, we have seen solidification in a mold previously, but this is a continuous casting process. And this is, as it moves, there are some water sprays. You can see that this shading is actually for the solid, and this part, this horizontal lines, that is the molten liquid. So delta is actually the thickness of the solid, right? The central part is kind of still hot, but the outer part where it's solidifying, the temperature is a little lower because you are water cooling the mold. Then there is withdrawal of this with the help of some rollers. So this is drawn like this. Okay, so this is plastic screw extrusion. So there is a screw, and you give a feed from here, and this is a heated and cooled surface. You get the extrudate, which is a die. And this is injection molding. Okay, I think all of you know this, but just wanted to show you to remind you that there are thermal processes involved, right? Heating, cooling, phase change, right? So thermal engineer has a role to play, but obviously there are other aspects also. This is a drawing of optical fiber. So there is a glass rod which is like drawn into this and then taken out using a pulley. Okay. This is solar power generation. So this is solar energy gets received and then it's sent back to this boiler. So concentrated on this boiler, and then the water here, there is water flowing here, which gets heated and gets converted to steam, and that can run a turbine. So instead of using a coal-fired or gas-fired boiler, you're using solar power. And this is a nuclear powered arrangement. So there's a nuclear reactor which basically replaces the usual boiler. So again, you have the same thing. You have high pressure, low pressure turbine. You have condenser. You have pump, and all that. This is another problem which we indirectly saw some time back. Actually, last class itself, where we need to cool electronic components. So there can be electronic circuit boards. So these are like stacks of electronic circuit boards, and you can cool this with the help of airflow. So there are many other means of cooling electronic circuit boards. There can be liquid cooling also, but this is just one example where there is conduction. So this is solid part, so there is conduction. There is also convection. Okay, then there's some fan which is blowing this air. So some characteristics of the fan also. Ultimately, our objective is, remember, to limit the temperature of the electronic components to some reasonable value up to which it can perform properly. Right? Yesterday I mentioned 80 degrees Celsius. I just said 80 degrees Celsius. It doesn't have to be 80 degrees Celsius. It can operate maybe at 115 also. Okay, depends on the particular circumstances for the particular setup that we are talking about.